Hi, today we are reviewing Newton's laws. So Newton's first law is also known as the law of inertia. Now with it, an object continues at its current velocity unless an unbalanced force acts on it. So an object in motion will stay in motion, continuing in the same direction at the same speed forever unless it has an unbalanced force acting on it. Similarly, if an object's already at rest, unless an unbalanced force acts on it, it's going to stay at rest. Now, in this course, an unbalanced force is also often referred to as a net force or sum of forces. Now, Newton's second law states that change in velocity per second of an object is proportional to net force acting on it and inversely proportional to mass. So in other words, we're going to have acceleration in the direction of the net force, and from kinematics, we know that the change in velocity per second is our acceleration. Now, based off of what is on that previous page, we end up with the following formula. Sum of forces is equal to mass times acceleration, where sum of forces is a net force acting on our object in newtons, or our unbalanced force. M is our mass, which represents the amount of matter in an object and is measured in kilograms. And A is our acceleration and is measured in meters per second squared. So we'll look at a few examples that utilize that formula. We have a force of 48 newtons acts on a mass of 8 kilograms. We want to know what is the acceleration of the object. Now we know sum of forces is 48 newtons, mass is 8 kilograms. We're looking for acceleration. So this is writing out the information that we're given in the question. Now we have sum of forces is mass times acceleration. We want to get acceleration on its own. So I would divide both sides by our mass. So that gives us sum of forces divided by our mass equals our acceleration. At this point, I'd substitute our values in. So we have 48 newtons divided by 8 kilograms. And that's going to tell us that our object is accelerating at 6.0 meters per second squared. Next, we have an object of mass 3 kilograms accelerates at 4 meters per second squared to the north. We want to know what force is acting on it. So we'll write out our information that we're given in the question. So we have a mass of 3 kilograms, an acceleration of 4 meters per second squared, and we're looking for sum of our forces. Now in this case, we can just go straight to our sum of forces as mass times acceleration. Don't have to bother rearranging it at all. We can just substitute directly in. So we've got 3 kilograms times 4 meters per second squared, which gives us a sum of forces of 12 newtons. Next example, when an additional force acts on a car, it speeds up from 12 meters per second to 18 meters per second in 3 seconds. If the force was 5,000 newtons, what is the mass of the car? So once again, I'll start by writing out the information we have. We know our initial velocity is 12 meters per second. Our final velocity is 18 meters per second. We have a time of 3 seconds, and we have a sum of forces of 5 times 10 to the 3 newtons. Now we're solving for mass of vehicle, but we know we're also going to have to solve for acceleration. So looking at the information we're given, I would look at our kinematics formulas and find that V equals V naught plus AT has the variables that we're looking for when solving for acceleration, because we have our final velocity, we have our initial velocity, and we have our time. So we just need to rearrange to get acceleration on its own. So first I would move the initial velocity to the other side by subtracting it over, and then we'll divide both sides by our time. At this point, substitute our values in, follow bed mass, and we get 2 meters per second squared. Now we'll look at our force equation. So sum of forces is mass times acceleration, and we want to get mass on its own, so we'll divide both sides by our acceleration. At this point, we'll substitute our values in. So we have got 5 times 10 to the 3 newtons divided by 2 meters per second squared. And that gives us 2,500 kilograms. Okay, so on to Newton's third law. Newton's third law is for every action force, there's an equal and opposite reaction force. So in other words, we might have two forces where we have F1 is equal in magnitude but opposite in direction to F2, hence why we have a negative in this sign. I have a couple drawings representing this. So if in a rocket launch, we have an action force, which is a fuel being pushed down off a rocket, while if a reaction force pushes the rocket upwards. Or we have a gun being fired, your action force is a bullet is shot, and the reaction force kicks the gun back. Now, if more than one object is being accelerated, Newton's third law is used to determine how each of its accelerating objects is affected by an applied force. So we'll look at an example of that. So we have a tractor pulls a crate along a horizontal surface with an applied force of 8,000 newtons. The tractor has a mass of 2,500 kilograms, and the crate has a mass of 1,000 kilograms. This motion is opposed by a friction force of 1,000 newtons, which I should state is acting on the crate. We're going to find the net force on the system, the acceleration of the system, and the amount of force that the tractor is applying to the crate. So first thing I would do is draw out our situation. So we've got a tractor here. We have that's moving forward with a force applied of 8,000 newtons. It has a mass of 2,500 kilograms. We don't know the force of tension between the tractor and the crate. The crate's 1,000 kilograms, and we have a frictional force of 1,000 newtons acting on this crate. So first thing we are asked to solve for is the net force of a system. So we'll refer to this diagram. Now, the tension force between the crate and the tractor, because it acts in both directions, won't affect the overall net force on the system. So we only have two forces here that will affect that net force, and that's our force applied and force friction. So we'll write down those values. So we're trying to find our sum of forces, and we're given our friction force applied. Now our sum of forces is just the addition of all forces in a plane. So we've got sum of forces is equal to force applied plus our force of friction. We'll substitute our values in, and we get the net force acting on our system is 7,000 newtons, which we can write as 7.0 times 10 to the 3 newtons to get to a correct amount of significant figures. Now, our acceleration of a system, we know our net force, we know our force of friction and force applied, but we also know our masses, which we need our masses to get the acceleration of a system. Now, because our net force is accelerating both objects, we'll be utilizing both masses. So we've got sum of forces is mass times acceleration. Rearranging this a bit, we divide both sides by mass, substitute values in, substitute MC and MT in for our mass, so adding those together. At that point, we substitute our values in, and we find that we have 2 meters per second squared as our acceleration. Last purpose was finding the tension force being applied to the crate. So if we look at just the crate, we have a force of friction acting on it, and we have the tension force. We also know the mass of the crate and the acceleration of the crate. So we know our force of friction is negative 1,000 newtons, so mass of crate is 1,000 kilograms. We also know we have an acceleration of 2 meters per second squared. We can look at our sum of forces in this case, which we know is force of tension plus force of friction. Now we want the tension force on its own side, subtract the force of friction to the other side. Now our sum of forces we can write as MA. So we've got MA minus force of friction equals FT. Substitute our values in, and we get our tension force is 3,000 newtons. Going to appropriate amount of sig figs would be 3.0 times 10 to the 3 newtons.